Today we are delighted to have Stephen Wolfram, a legendary scientist of our time who has benevolently agreed to give an invited lecture on the Ruliological view of cellular automata. I see he has joined. A very good evening to you, sir.
Thank you.
Although he needs no introduction, but for the formality of the program, we have to introduce him briefly. Stephen Wolfram is a pioneering scientist, physicist, and author of A New Kind of Science, whose work created a paradigm shift in cellular automata research. He published his first scientific paper at the age of 15, had received his PhD in theoretical physics from the California Institute of Technology at the age of 20. In recognition of his early work in physics and computing, Wolfram became the youngest recipient of MacArthur Fellowship in 1981. Stephen Wolfram is the founder and CEO of Wolfram Research, creator of Mathematica, Wolfram Alpha, and the Wolfram Language. In 2012, he is named as a Fellow of the American Mathematical Society. He writes regularly about his activities and thoughts on his Stephen Wolfram writing site. So over to you, sir. We are eagerly waiting to have a great talk to listen from you.
Great, thanks very much. Well, it's very cool to see that you guys are studying cellular automata so much. I have been a huge enthusiast of cellular automata now for about 42 years. And I thought I might tell you a little bit about some of the journey that I've been on studying cellular automata and the things that have come out of cellular automata. And I'll even tell you some things that I've been working on the last few days related to cellular automata. So maybe I should get started at the beginning. Oops, no, you're not letting me screen share. Can you set it so that I can screen share? Otherwise.
Yeah, sure, sir. Just a second.
No problem. Not yet. If you need to, you could make me a co-host or something. That will probably work.
Professor Sukanto Das, can you please make him a co-host?
Yes.
And you're also welcome to record this if you want.
Yes, maybe it's working.
Okay, all right.
Yeah, sorry.
I'm going to press the record button if you don't mind. Okay. All right. Well, let's see. As I was saying, my friends, cellular automata. I first got interested in cellular automata. I'd been studying physics. I was interested in kind of how complicated things come to happen in the world. And I was sort of unsatisfied with the approach that one gets from studying mathematical equations and trying to solve equations to work out how natural systems work. At the time, I had been just involved in building my first computer language. And that kind of gave me the idea that maybe you could just build things in nature out of kind of computation. Thinking about cellular automata, I think my first was sort of typical of my early 1981 style approach to cellular automata. These days, gotten a lot easier. In Wolfram Language, for example, we can say, let's talk about some cellular automata. Let's say we have a particular cellular automaton rule. Let's say, I don't know, rule 254 or something. We can say, just show me a picture of what that rule corresponds to. This is a one-dimensional cellular automaton rule. We just have a line of cells. Each cell is either black or white. And this table tells us the program for specifying what the new color of the center cell will be. So then what we're interested in doing is working out, just doing the computer experiment. This is kind of like, I view it as being kind of the most basic, turn your sort of computational telescope to the computational universe and see what's out there. And this is kind of the sort of most simple version of that. And let's say we do a cellular automaton like this, and we say, just show me that. Let's plot it with a mesh there. There's the result of applying that rule, starting off from just one black cell. And as cellular automaton enthusiasts, you've seen many of these, I'm sure. The question is, if I type in some number here, will one immediately recognize what that pattern is just by seeing it? I think I have probably used up some parts of my brain's visual memory by knowing immediately a bunch of these cellular automata. But the question that sort of the experiment that launched a lot of what I've done is just the most obvious kind of computer experiment. The experiment is just look at all possible rules of this type, the so-called elementary cellular automata, as I named them long ago. Let's look at all 256 rules of this type, and let's just see what they do. And now, of course, it's much easier to do that than it was, especially if I could actually type correctly. Much easier to do that than it was back in 1981. But here are our friends, the elementary cellular automata, and those of us who study cellular automata a lot probably consider many of these kind of our personal friends. There's some, that one there I recognize as, that's rule 18. Then my all-time favorite, rule 30, starting off from just one black cell, you get this kind of very complicated pattern of behavior. We could continue it, and we'd see that kind of complexity go on. And I'm so keen on the cellular automaton that for many years my business card has had a picture of that cellular automaton on it. And I consider it sort of the most interesting scientific thing I've ever had the good fortune to see. But we can go on and look at these other elementary cellular automata. There's rule 45, another one that has complicated behavior, just starting from a simple initial condition. There's rule 73. I showed you that earlier. And we can keep going. And as I say, there are things to study about the vast majority of these elementary cellular automata. The amazing thing is that, more than 40 years later, there is a huge amount we still do not know about even the elementary cellular automata. So, for example, I am just in 2019 set up some prizes to learn things about Rule 30. This is the Rule 30 pattern, and it's like, does the center column always remain non-periodic? Does each color of cell on average occur equally often? Does computing the nth cell require at least about order n of computational effort? We do not know the answers to these questions. It's been 40 years. We've made sort of slow progress on pieces of this. These are the types of questions that would be profoundly interesting to know the answers to. So I said cellular automata have, to me, they are kind of the minimal models that have the feature that you've defined space and time. There's just this grid of cells. There's a sequence of steps in time. You have a discrete set of values. And then with those simplifications, you have cellular automata. And needless to say, over these years, cellular automata have found applications in just a huge collection of different areas, both as models of things and as things to study in their own right. And it's been interesting to see that this, in a sense, you can start from a model of a thing, whether it's studying plant growth, or whether it's studying catalysts in chemistry, or whether it's studying some mathematical question. You can start from these things, and you can go from sort of a model that's been made, you can kind of make a meta model of that by saying, well, we don't really need all these details about the exact thermal conductivity of this thing. What's the essence of what's going on in that system? And very often you find the essence of what's going on can be captured by a cellular automaton. And I kind of call this process of going from a practical model that one makes with all kinds of details and so on, to finding out the essence of that model and finding the sort of computational essence of the model. I call that process kind of meta modeling. And so then the question is, what do you end up with when you've done this meta modeling and you've gotten to the point where you have this very minimal, simple set of rules, what then do you do? Well, I've been interested in this question for a very long time. And as I say, I started studying cellular automata more than 40 years ago now. I've just recently kind of come up with a name for the process of what one is really doing when one is studying these simple rules and their behavior. I call it Ruliology. It's studying simple rules and what they do. And it's in a sense, it's kind of a fundamental field of science. It's a field of science that is, in a sense, more fundamental than mathematics. Mathematics deals with specific kinds of rules. We'll talk about that a bit more later. Ruliology is the study of simple rules of any kind and what they do, what their consequences are. Those rules tend to be rules that are defined computationally, and the way that you study them at first is to do computer experiments, to just sort of turn the computational telescope towards this kind of Ruliological universe of possible simple rules and see what's out there. Now, one of the things that I think is rather interesting is that over this last 40 years and so on, there's been all sorts of interesting work done on cellular automata, other systems based on simple rules. We can talk about some of those in a bit. And in a sense, this field has had, that there are many interesting things that have been done, but it is still a very fragmented field. It's really great to see you guys doing a conference devoted to cellular automata. That's a really valuable thing. But I think this general field of studying simple rules and what they do, it deserves to be a field of science. And not only is it a field of science, it is a very fundamental field of science. It's a field of science that, as I say, is kind of a generalization of mathematics in the sense that it does not just deal with the specific rules that mathematics concerns itself with, but with all possible kind of computational rules. It is, in a sense, a foundation for computer science. Computer science tends to be involved in creating programs that have specific purposes, that where we're engineering something to do a particular thing. Ruliology is the study of kind of computation in the wild. What do programs that you have just picked from the computational universe without specifically engineering them step by step? What is computation in the wild? What is that like? What is kind of the natural science of computer science? It's different from the sort of the engineering discipline of computer science, but it is a foundation for the engineering discipline of computer science, because to know what's out there in the computational universe is to know what raw material we can make use of when we start creating specific algorithms and so on. And one of the things that I think has been very valuable, we've certainly used it a lot, is this concept of mining the computational universe. There are all these things out there, Rule 30, Rule 45, Rule 90, all these different cellular automata, a zillion different possible rules. And the question is, can we find, are they useful for things? They do very interesting things from a kind of purely scientific point of view. Can we use them for technology? And Rule 30 is a good random number generator. We can go on and list other kinds of rules that are good for different kinds of purposes. Can we make use of these things? Can we kind of mine things from the computational universe for our particular technological purposes? And this has been a very valuable direction to just say, first you do the Ruliology to say what's out there in the computational universe. Then you're doing, in a sense, the kind of the mining of the Ruliological world of the computational universe to say, let's pull this in for specific technology. Now, in a sense, the kind of the whole world of deep learning and neural networks and so on, that is kind of an on-ramp, in a sense, to this world of mining the computational universe. When we think about looking at simple cellular automata and so on, and saying, oh, this cellular automaton is an amazingly clever way of doing this particular kind of useful technological task, that's something where we're really mining we're mining very deeply in the computational universe. What happens in neural networks, for example, is we say, well, we've really got this thing that is defined by a million real numbers or something, and we're going to tweak those real numbers so we get the thing that is sort of close to what the thing would naturally have done, but we're going to make it so we train it to the particular thing we want. That's, in a sense, a it's a very practical thing to do. It's kind of making use of calculus and making use of the idea that, you know, you can make a small change and move towards an optimal point. The case for sort of arbitrary things from the computational universe, it's a more difficult case. It's and really pretty much the only way we so far know how to do this is through kind of things that involve exhaustive searches and various kinds of approaches like that. One of the things that I think will be sort of a major coming attraction in the next, I don't know how long it'll be, decades of studying the computational universe is a series of what I suspect will be breakthroughs in understanding how to take some of what's been learnt from the world of deep learning and apply it to being able to actually find things in the computational universe, to be able to perhaps somewhat incrementally kind of explore the computational universe rather than doing it. So those are, so this sort of brings me a little bit, just for fun perhaps, to you know, what cellular automata have I done this week? You know, as I say, it's been 40 years, and yet I find myself continually coming back to cellular automata as the finest sort of minimal examples of these phenomena from the computational universe. So this week, and I'll explain some of the backstory to this perhaps, I've been writing something about the concept of motion. How is it that things manage to move in the universe, in physics? And I'll talk about that a bit in connection. Oh, okay. And so in this question about motion, I've been led yet again to cellular automata as an example of what's going on. And let me just pull up. I am muted. I got muted there. Sorry about that. So in any case, one of the things that, so in kind of the story of my kind of intellectual journey, starting with cellular automata back 40 years ago, developing kind of in the direction of trying to understand complexity in nature, and then having done that, realizing that one of the things that was critical was sort of having the tools to explore the computational universe. And that led me in 1986 to start building Mathematica and what's now the Wolfram language, as a way to kind of, in the end, have a sort of computational language for describing things in the world. And that includes for Wolfram language, describing, you know, cities and algorithms and all sorts of other kinds of things about the world. We're sort of building this computational language to make a notation for representing things computationally, in a little bit the same kind of way that mathematical notation was invented maybe 400 years ago, to try to represent kind of have a systematic way to represent mathematical concepts. I view the Wolfram language as sort of a bridge between this computational universe of possibilities and the things that we humans care about and want to talk about, and how we represent those things computationally. As I say, a lot of what the Wolfram language is doing is dealing with things in the world, whether they're images or graphs, or whether they're things about chemicals and biosequences and whatever else. But the sort of purest thing that the Wolfram language deals with is sort of a representation of raw computation in such a way that it's very convenient to explore the computational universe. I mean, I built Wolfram language first and foremost so I could be a user of it. And it's fortunate that millions of other people are users too. But for me, it was built sort of in large measure to provide the best kind of way to explore the computational universe. And so, having built that, I wanted to actually use it. And so I started in 1991, sort of exploring the computational universe beyond cellular automata and trying to see whether the phenomena that I had first found in cellular automata, like the complexity generated by Rule 30 and so on, how general were those phenomena? And the main conclusion was they're extremely general. They apply to Turing machines, substitution systems, register machines, symbolic systems, things in 2 dimensions, things that have infinite numbers of dimensions, things involving tilings, things even involving partial differential equations, and things that show up in kind of the traditional mathematical science. And so and I discovered that cellular automata, particularly cellular automata, but also some of these other systems, were suitable as models for many kinds of things in physics, fluid dynamics, in biology, biological growth processes, and so on. That this process of meta modeling, I didn't have that name for it at that time, of going from one of these systems, from even existing models of these systems, and saying, what is the essence of that model? What is the sort of computational essence of what's going on? That led me over and over again to cellular automata. And then I realized that sort of these phenomena that I'd first seen in cellular automata that were also visible in all these other kinds of systems, these phenomena, and the big one that I defined then as the principle of computational equivalence. Essentially, the idea there is when you look at something like Rule 30, you can characterize it by saying it does a computation. It starts from its initial conditions, it goes, it computes, and that's the process that it goes through as a computation. And then the question is, well, how sophisticated is that computation? And the point of the principle of computational equivalence is, as soon as even sort of the picture you get is not obviously simple, you've probably got a computation going on that is sophisticated as any computation. So you might have thought that with these very simple rules, you get only very simple computations. As you put in more sophisticated rules, you get more complicated computations, more sophisticated ones, and so on. But the principle of computational equivalence says that isn't true. As soon as you get past the threshold of sort of not obviously simple behavior, you are in this world of equivalent computational sophistication. And so that has many consequences. One of them is the phenomenon I call computational irreducibility, which I think has been a really core phenomenon that is this idea of, well, okay, if you want to predict what's going to happen in one of these systems, if you have Rule 30 and you're trying to predict what's going to happen after 1 billion steps, how do you do that? Can you find a formula that will allow you to kind of jump ahead and work out the 1 billionth step? Or are you stuck having to go step by step, as Rule 30 itself does, and figure out the next step? Computational irreducibility is the idea that in many systems, there is no choice but to just go step by step. It is an irreducible computational process to find out what's going to happen. Now, that's somewhat at odds with what one traditionally thinks about in the exact sciences, where you say, oh, you know, the Earth might go through 1 million orbits in some idealized planetary system, but we can just fill in the number 1 million in a formula and work out what will happen. We don't have to trace all those 1 million orbits. We can kind of jump ahead and reduce the computational work necessary to find out what happens. What computational irreducibility says is that that often won't be possible, that there is no way to predict what's going to happen in a system other than by essentially running it and seeing what happens. The reason that follows from the principle of computational equivalence is this. If you imagine us trying to predict what a system is going to do, what's happening there is we are putting ourselves in competition with the system itself. We, with our brains, computers, mathematics, whatever, are trying to do a computation to figure out what's going to happen in the system. Meanwhile, the system itself is doing computation to work out what it will do, so to speak. And what we'd be claiming if we said we can reduce that computation, we can jump ahead, is that the computations we can do are fundamentally more sophisticated than the computations that these systems do. And the point of the principle of computational equivalence is to say it won't be that way. These systems do computations that are just as sophisticated as the ones that we are capable of doing. And over the years, we've gotten more and more evidence of the principle of computational equivalence. The Rule 110 cellular automaton is a nice example of something where we know there's universal computation. That's sort of one of the things that you need to be able to show to say it really is computation as sophisticated as anything. In 2007, there's also the 2-3 Turing machine, the very simplest universal Turing machine that I kind of, that the principle of computational equivalence kind of says this Turing machine should be the very simplest universal Turing machine. And we put up a prize for that, and a young chap called Alex Smith proved that, yes, indeed, that Turing machine is universal, providing another piece of evidence for the principle of computational equivalence. So, once you have this principle, it just has many, many implications. And we'll talk maybe a little bit later about its implications for sort of fundamental things to say about the universe and physics and so on and beyond. But computational irreducibility is one of the consequences of the principle of computational equivalence. Computational irreducibility has many, many consequences in science. I mean, I view it as being, for the study of the computational universe and Ruliology and so on, it is a fundamental concept in the same way that things like energy and momentum and so on are fundamental force, are fundamental concepts of things like Newtonian mechanics. In a sense, Newton was very lucky back in 1687 and so on to get to study mechanics of, he picked well the thing he studied. Had he tried to study fluid mechanics, he never would have concluded that there was this sort of simple set of laws, simple reducible behavior. He would have been stuck looking at fluid turbulence and sort of not having a way to formulate simple laws. He had managed to slice off a piece of the physical world where there is computational reducibility. But most of the computational universe and much of the physical world does not have computational reducibility. It's instead computationally irreducible. And that has consequences sort of both philosophical and practical. But I think it's something where we're just beginning to see. I mean, it's beginning to be important for questions about computational law and things like this idea of computational irreducibility and what that means for sort of whether the AIs can be expected to do what we think they'll do and so on. But the thing that, in a sense, computational irreducibility seems like it's a limitation. It seems like it's telling us there's things we can't know about the future. There's things where we can't really make predictions other than by essentially running the explicit simulation. In a sense, from a sort of a human point of view, there's some satisfaction in this idea of computational irreducibility because, we lead our lives, they correspond to things happening through time, and we can think about the things we're doing as sort of playing out a computation. If everything was computationally reducible, we'd be able to say, and the answer is 42 or something. We'd be able to sort of always jump ahead, and we wouldn't have to go through the actual steps of sort of leading our lives, so to speak. And so, in a sense, computational irreducibility is what makes it the case that the passage of time is truly meaningful. The passage of time is achieving something that is an irreducible kind of computational thing. So it's kind of both a limitation on what we can know in science, and it's one that is of fundamental importance, both philosophically and for the practical doing of science and the practical thinking about things like policies and technology around science and so on. But it's also something that has, that's kind of the negative is what we can't know. The positive is it means that the passage of time is sort of in some sense truly meaningful. Well, in any case, I think that the I wanted to kind of I was talking about the cellular automata this week. So it's something that's come out of our physics project, and the question is, in physical space, how is motion possible? And that led me, let's see if I can find it here. One of the things we've been doing with the physics project, which I think has worked out terrifically, and I really encourage people to do it, is kind of radically open science, so to speak, where we're live streaming many of our kind of working sessions, studying the science, and we're putting up the sort of very quickly. So let's see if I can find one here. Okay, there we go. There's a Cellular Automaton searches 05. Let's see what that. Okay, oh boy, this was, I think, too big for this. Okay, well, you see lots of friendly cellular automata here. And this is, I was searching for cellular automata that would be good examples of essentially the phenomenon of motion. What is motion? Well, in a general sense, motion is the fact that something can change its position and still be the same thing. In our model of physics, space is made up of this kind of giant network of atoms of space. And whenever something moves, it is being made of different atoms of space. So it's kind of the fact that a thing can exist and move without change is not a trivial fact. In something like a fluid, you have the same kind of issue. The individual molecules are different molecules, but yet some vortex can move through the fluid, and we have a sense in which that vortex has an identity as it moves through the fluid. But it's kind of a more extreme case in our study of physical space. But as a kind of analogy for that, I was interested in when are there things in the cellular automaton that you can kind of identify as things that have a particular identity and yet kind of move across the system, and what, you know, as is so often the case. I mean, these were just cellular automata that I found in a big search just in the last couple of days, and one of the things that's remarkable is you say, well, I kind of know about these structures that can propagate and so on, and I sort of know about those, but then you say, well, let's kind of home in on more detail about what's really going on with those things, and you realize my kind of personal mantra for this has become the computational animals are always smarter than we are. That is, anytime you thought you knew what was possible, oh, you'll get these structures, or you get this, you get that. When you actually look sort of Ruliologically, so to speak, you actually study the computational universe, you discover there are things that happen that you never guessed. In a sense, you know, these computational animals, they always outthink us. In a sense, this is a symptom of computational irreducibility, that we can't know what's going to happen before we actually try it and see. And, you know, there are things that where I was kind of, you know, where there are like structures that last for a limited time, but other things are going on and so on. There's all kinds of things that one can start to analyze here to kind of begin the process of understanding this fundamental phenomenon of motion, which, you know, you might have thought that the question of what motion is would have been answered in antiquity. And indeed, there were thinkers in ancient Greece and so on who thought about this question. But it kind of, the things got lost somewhere in the 1600s when people kind of had the model of space that that emerged from Euclid and so on, where space is just this background and you get to put things anywhere you want in space, rather than space having a definite structure. Well, so maybe I should say something about, I've been talking a bit about what, well, this is an example of, let me see, I maybe can show you one thing. I think I just got, just before this event, a research assistant of mine just sent me, let me look here whether I can pull it up. Just for fun, I'll show you the absolutely hot off the press thing, which I literally just got and haven't even looked at yet. This is a search in various, okay, this is searching various different cellular automata for structures that have, for these definite structures that kind of perpetuate themselves. But the thing that's, in a typical, this is a kind of typical Ruliological investigation. You're starting off doing the computer experiments, you're then building some analysis technology. Then the end result of this will be that you learn, you do various experiments, you come up with various empirical conclusions, and then in the end, you end up with principles about what's going on that potentially inform some very fundamental questions, like the question of what motion is, for example. But that's kind of a typical thing in Ruliology, that you're going through that process from experiment to analysis to kind of synthesis of what's happening, and then potentially to very powerful application. Because in a sense, what's going on in Ruliology is that you're sort of underneath everything. You've sort of meta-modeled down to the point where you're really dealing with this sort of fundamental computational essence of what's happening in these systems. And so in a sense, it's a very high leverage thing to be studying. As soon as you say something about sort of this general Ruliological kinds of level, you can immediately say, well, that has consequences in all these different areas and all these different fields and so on. So it's a really powerful thing. And I've noticed, for example, with the elementary cellular automata, that the thing that's been remarkable is any one of those that one might have picked years ago and said, I'm going to be an expert on that. I know some people here have become really expert on Rule 90 and Rule 150 and so on. Those things have applications in all kinds of places, And by having kind of taken this very minimal model and studied it in detail, that's something which will have consequences, sort of downstream consequences. And that's one of the just great things about Ruliology and about cellular automata is the fact that you're studying the sort of the lowest level. You're studying the essence of things. And so that means that whatever study you do, even if it is a sort of theoretical study at this point, you can be pretty certain that that will have kind of these practical applications and consequences. You know, I kind of view Ruliology as it is right now, and a little bit like sort of chemistry of 150 years ago or something, 130 years ago, where people were studying this compound and that compound and the other, and you study them as a matter of basic science. And then over the course of time, more and more applications are found where this is important for making plastic, or this is important for that, and so on. And I think that's the picture that you get with these kind of Ruliological investigations. Well, maybe I should say a little bit about some of the things that, again, some other kinds of places where, like, let's say in the last year, where have cellular automata appeared in my life in the last year or so. And, you know, it's kind of interesting, again, that in lots of different things I study about questions about why the universe exists and questions about lots of things about physics and so on. Here's an example. This is one that actually came out of blockchain. This is it's actually something I studied because it's important for kind of the sort of moving towards a more distributed version of blockchain. This is the problem of distributed consensus. You've got a bunch of elements, and you've got, let's say, you want to say when more than half of them are one color, you want to know what that color is. And so, needless to say, there we go, we're looking at cellular automata, and we're looking at, for example, these particular cellular automata where if you have more than 50%, in this case, red cells, the thing becomes all red. If you have more than 50% yellow cells, it becomes all yellow. You have, this is kind of a very minimal example of a phase transition. And you get to see right at the 50% point, you get the characteristic feature of phase transitions, which one studies in much more elaborate ways in traditional statistical physics, where there's kind of an infinite hierarchy of nested patterns where it can't sort of decide whether to go yellow or red. But what's interesting here again is, okay, so you want to make a distributed blockchain-like system, and this is a very practical thing. People are using cellular automata to do this. There's a blockchain called NKN, which I kind of like because it's very reminiscent of the, you know, my big book is called A New Kind of Science, and NKN stands for a new kind of network, and is very much based on thinking from NKS. But one of the things that's involved there is the practical problem of finding a good distributed consensus algorithm using, in fact, cellular automata. And so again, we can do kind of a Ruliological study. Let's go explore the computational universe of possible cellular automata and find the most efficient one that achieves this kind of distributed consensus. You can kind of go down here, and there are all kinds of cool things that you find sort of exploring that. It's sort of interesting. This one here is a constructed rule that's somewhat more complicated. As you go down here, you get simpler rules that have slightly more ornate behavior, but still have this consequence of achieving distributed consensus. And you can kind of, you know, it seems like in the sort of, there's a pattern of doing Ruliology, which is, you know, you study what happens with particular initial conditions, you look at pictures of that, you then might study sort of what happens with all possible initial conditions in a finite sized region, and then you've got state transition graphs, and here's bigger state transition graphs, and so on, and that and then that's sort of a typical Ruliological thing to study. This is now the cellular automata in more than one dimension. That's a 2+1 dimensional display of that cellular automata. And this is all, by the way, if you ever look at things I've written, you can always click any picture, you can paste it into a Wolfram notebook, and you should just be able to run it and get the same picture. Well, there's a random number involved there, so you don't get exactly the same picture. Oh, maybe you do, actually. I think you do get the exact, there you go, because the random number is seeded here. So you get the exact same picture that was in the thing I wrote. And this, by the way, methodologically, having this Wolfram language code be something that is in documents, and every time you see a picture, you know, you can just click on it, you get the code. I can now start, modifying this. I could say, I don't know why that's a funny color there. Let's see, let's make that its color. I could say, for example, let's do it for 30 steps instead of 10 steps or something. There we go. Okay. Or I could change some aspect, I could change this random number seed here, and I'll get some different pattern. It's really, really valuable, really powerful to be able to take essentially this computational notation. And, it's rather easy to read this notation. We're saying, we're just saying we're making a 3D array. Okay, we've got a bunch of silly details here about mesh styles and so on. We could make this a bit more elegant by just taking all of those and iconizing those so that we don't explicitly show them here. We can do that. And now we're saying, okay, we're using random choice 0 and 1 with those probabilities. And this is the rule we're using, dimension 2, neighborhood 5, totalistic rule 56. Maybe I could change these probabilities here to 0.8, 0.2, 0.8, for example, and rerun the thing, and so on. It's extremely valuable, and this is kind of what I've been building towards for 40 years, to have this language in which one can express oneself computationally and have it be something that both we can read as humans and the computer can execute and let us explore. And then in terms of presentation, it's extremely valuable to have something where right within your the things you write, you immediately are presenting them in a way that people can follow up from. And by the way, I should say that our summer school and winter school, and I just encourage people, if people are not aware of our Wolfram summer school, which has been going now for 20 years, where people study all sorts of things about the computational universe and about science and technology using kind of our computational methods. I encourage people to think about participating in that. We also have a high school summer camp for high school students, which this year will again, unfortunately, be virtual, but that gives more opportunity from folks. For example, in India, we've had a bunch of great students from there over the years to participate in that. But the thing I was going to say about that is one of the things that we see at the summer school, and we also have a winter school around our physics project, is the fact that when people do projects there, and the goal of those schools is to be able to have people do an original project in the course of the school, they kind of start from, for example, things I've written where they just say, take the Wolfram language code, take it for this case, now go start exploring from that. And it's a very powerful way to kind of build a field by kind of being able to have kind of the steps you can go sort of step by step, by really making use of not just reading somebody's paper, but also being able to actually take the Wolfram language code and both be able to read that code yourself and be able to actually execute it on a computer. And by the way, I should say that I could take this notebook. This is just a standard Wolfram notebook, and it can be a mixture of I've kind of very big on this idea of computational essays, which are a mixture of kind of text together with executable and readable code. I mean, that's the important thing about computational language as opposed to programming languages. Our computational language is intended to be read by humans. It's not just something for a computer to execute. It's something that intends to be a notation, kind of like mathematical notation, that represents something that's being talked about. But I could take this notebook and I can publish it to the cloud, and then when I've done that, it's anybody can immediately go look at it in a web browser and go start interacting with it. We could I could post this, or we could just, for fun, we could put up that. But I'll post it later. So in any case, that's kind of a methodological thing. Is, we built this language that allows one to express kind of Ruliological ideas and to be able to sort of pass them on to other people. Anyway, I was just showing you kind of cellular automata for this year's Cellular Automaton hall, so to speak. So this is more about distributed consensus. As I say, this is very directly applicable to these questions about blockchains, and we're then looking at the case when there's noise and how that works. This is kind of this is representations of sort of all possible evolution paths and so on. This is lots of things here. Again, this is all kind of Ruliology in this particular case in the service of blockchain studies. But to give you another example of something, this is a problem that I studied, sort of a 100th anniversary type thing. The problem of tag, which is you take these a sequence 0, 2 blanks, and then a sequence of symbols, and you just do this pattern replacement. This is just Morphing Language code here that tells you to chop off the first 3 elements and add 2 zeros if it starts with a 0. If it starts with a 1, add 1, 1, 0, 1. What does that system do? This chap, Emil Post, back in 1921, realized that if he could only solve the problem of what systems like this did, he could solve all of mathematics. The only problem was it was really hard to solve the problem of these particular kinds of systems. And it's another kind of Ruliological problem. You can kind of look at the sequence of what's being generated and so on. And it turns out it's really complicated. And it turns out a bit like with cellular automata, these pictures are looking very cellular automaton-ish. The question here in particular is, well, these are state transition diagrams for tag systems, are asking, does it actually terminate? That was the thing that Post was really interested in. Does it terminate? He didn't know about the unsolvability of the halting problem. That came much later, although he effectively discovered that. But these are things Post tried to do, and you can find out that, well, actually, it's pretty complicated what happens. This is kind of a Ruliological investigation showing, in this particular case, starting with Post system with some particular initial condition, this kind of shows the progressive states that you get, and that it eventually, in this particular case, becomes periodic. But things can get really complicated. You can go on for 643 billion steps before you determine what's going to happen. And then again, there's sort of principles here. Are these really like random walks? What's involved in that? Can you compare them with random walks? Well, then I'm asking, so how do we understand the phenomenon here? Well, let's go back to cellular automata, because in cellular automata, we already see many of these phenomena. So for example, this kind of random walk, what's it going to do? Just in our friend Rule 30, we already have one of those. The line between kind of the region of randomness over here and the repetitive region, that is something which is like a random walk. It's actually a biased random walk. My friend, the physicist Richard Feynman, when I first discovered Rule 30, he was like, I'm going to prove Rule 30 is regular. I'm going to prove I can work things out about Rule 30. And one of the things he concentrated on was, can he predict can he show that this particular front here executes a random walk? And actually, I might be able to find, let's see. Hold on one second. I might be able to find. Let me see. Here we go. Yes. Okay, that's a younger me with Dick Feynman. Okay, here we go. This is Dick Feynman trying to work out. You can kind of see the cellular automaton, little sort of his version of physicist attacks cellular automaton type thing, and trying to work out. And of course, then he's he's reduced to actual computation and trying to work out, what is the rate? What is the, can you estimate what actually happens at that front? And here I think were a few of his estimates of that. His guess was, and mine too, that it would move at a speed of a quarter of on average, a quarter of a cell per step. Well, you can ask let's see, yeah, here we go. You can ask what actually happens. It's not exactly 0.25, it's 0.2481, and then it keeps going. So this is one of these things where you do the experiment, you discover the computational animals are always smarter than you are. Dick Feynman and I both, we didn't get it right. We didn't manage to estimate what this was. We still don't know. One still doesn't know what the actual average rate of that random walk is. But it's interesting that just like in this post-tag system case, where we get what amount to random walks, we're already getting that in the Rule 30 cellular automaton. And even in that case, we can't figure out what's going to happen. These are other examples of cellular automata that have the property that their boundaries, their full boundaries, show apparent randomness. This is a cellular automaton where the question is, does it grow linearly? Does it grow something else? What's the rate of growth? Again, more cellular automata here. They're the sort of foundational models for the examples that one can use. And there's, in this particular case, I'm showing connections with number theory. We're getting to the 3n+1 problem. We're getting to the Riemann hypothesis. These are all connected to tag systems and sort of more indirectly to cellular automata. I think maybe I show a few other cellular automata in here. But this is sort of typical Ruliological fare, studying kind of the computational universe and what's out there. And then, are these? No, those are tag systems. It's hard to tell sometimes. Yeah, so lots of computer time spent trying to find about tag systems. Just another example of kind of Ruliology in action. Now, I might mention that, well, let's just see. Maybe I should talk. I'm going to, let me not spend too long here because I really want to have some questions and discussion. I just maybe mention a few other things. One of the big directions, okay, so let me talk a little bit about our physics project, because that's something that's kind of something that has emerged from kind of what we've studied with cellular automata, the principle of computational equivalence, et cetera, et cetera, et cetera. Eventually we get to kind of the physics project. Let me just go there. Let me just go through this extremely quickly. I mean, basically what we have successfully managed to do over the last couple of years, I think, is we kind of found what the machine code of physics actually is. What is the kind of underlying structure which underlies the physics we know? And sort of the key idea is to realize that space is not what Euclid thought it was. It's not just this sort of continuous background where you can put a point anywhere. Instead, space is made of something, just like fluids, like water are made of molecules. Space is made of atoms of space, which are abstract objects that simply have, the only thing one knows about them is they have an identity and they are related to each other. And you can represent those relations by a big hypergraph. And the point is that that hypergraph, when it's sufficiently big, it behaves locally like continuous space, just like a fluid, even though it has underlying molecules, behaves like a continuous fluid on a large scale. So the way this merges like that, time is kind of the progressive updating of this network. It's very much like a cellular automaton, except now there isn't a fundamental space that's been put in. Cellular automata are kind of the ultimate idealization of parallel computation, where you've defined what the kind of structure of space is. What we have in our physics project, I guess they're called Wolfram models these days, is this idea that we just have this hypergraph, and at every step we're looking at little regions of the hypergraph. We have a definite rule that says, given that there's a piece of hypergraph that looks like this, transform it to one that looks like that. And so time in the physical universe consists of the progressive computation according to these rules. And so one of the things that's very remarkable, even to begin with, is the fact that even though space and time work very differently in these rules, in the setup, it turns out the relativity and space-time and the structure of space-time emerge. And in particular, kind of general relativity, Einstein's equations for space-time and the curvature of space-time turn out to emerge in the same kind of way that the equations of fluid mechanics emerge from discrete information about molecules bouncing around. That was something I kind of first knew in the 1990s, was sort of an indication that this kind of direction might be on the right track. Well, the next thing is to realize, and this is where we kind of differ a little bit from cellular automata, these updates can happen anywhere. And the idea is that all we're saying is the update will happen whenever it can happen. And that means that instead of having a synchronous thing like in a cellular automaton, where we're progressively going one step through time to the next, we end up with something where there is an update whenever there can be an update, there is an update. And the result of that is that you don't have just a single thread of time. In a cellular automaton, there's a single thread of time, but in our physics project, there isn't a single thread of time. There's this multiple threads of time, multiple histories for the system. And it turns out that those multiple histories are what give us quantum mechanics. In a sense, the essence of quantum mechanics is this idea that, in classical mechanics, definite things happen. In quantum mechanics, many paths are followed, and then observers kind of sample those paths, and we can conclude probabilities about what might have happened. What ends up being the case is that in our models, there's this branching and merging of possible histories of the universe that takes place, and the observer, that's us, ends up being embedded in the system, also branching and merging. And so kind of the mystery of quantum mechanics ends up being a lot about how does a branching brain perceive a branching universe? Long story how that all works, but that's kind of the essence of how quantum mechanics arises in our models. And the thing that's really been great is that our models sort of plug into all these different directions in mathematical physics that have been developed over the last few decades, and they provide sort of a machine code for those different areas of mathematical physics and kind of ground them in something that really looks to be, this is the way the physical universe works. But this gives us a whole new area of what we call multi-way systems, of systems where there isn't just a single thread of time, there are multiple threads of time. Multi-way cellular automata, I just, poked my nose into multi-way cellular automata. We really know almost nothing about multi-way cellular automata. I wrote about multi-way Turing machines, and this is an ordinary Turing machine. This is a multi-way Turing machine, like a non-deterministic Turing machine, except that in a non-deterministic Turing machine, you're usually talking about, I want that one winning path that gets me to the answer. In a multi-way Turing machine, you're saying, I want to consider all these different paths, not just the particular one that lands me up at the place I wanted to get to. And I think here, if we go far enough down here, I think we're going to hit multi-way cellular automata, if I'm not mistaken. I think maybe hold on, this might be, you know what, I'm looking at the wrong place because I really need to look at a different post I wrote. Here we go. So this is, if I go to the bottom of this one, I will find these are actually, that's the Turing machine case, and here, cellular automata. So these are now cellular automata, which, like these models based on hypergraphs, this is like cellular automata, where instead of having a particular rule at every step, you say, let me follow any rule. Let me just trace out the paths where I'm following different rules on different steps. And I'm looking at kind of what possible behavior can I get. And I just started looking at this for cellular automata. By the way, these kinds of investigations of kind of what can I get by using this kind of non-deterministic or Rulial kind of system, what can I get relative to what I can get deterministically? This turns out to be essentially the P versus NP problem of computational complexity theory. It's kind of, you can geometrize that question. It's kind of asking, is the red piece here, which is the deterministic front, does it cover the gray piece in some appropriate limit? Well, okay, so anyway, there's this whole kind of new world of multi-way cellular automata that I've investigated almost not at all, that I'm sure will be quite rich. Multi-way systems in general, you can study extensively. This is multi-way systems based on numbers, where we're just saying, you know, at every step you can compute, let's say, just, it's just pure multiplication. I want a better example here. Yeah, 2n or n plus 1. And you're at each step, you're just taking one branch is 2n, another branch is n plus 1. What do you get? You get this complicated pattern, this complicated multi-way graph representing different behavior. This is a typical kind of Ruliological investigation. This is now sort of trying to explore multi-way computation. Now, this notion of multi-way computation or multi-computation, this is, again, something that sort of emerged from our physics project, and I consider it a truly fundamental feature of kind of the evolution of kind of scientific thought. I mean, I kind of, there's sort of this progression of different kinds of ways to think about making models of things. From antiquity, where the basic question was just sort of, what are things made of? Are they made of atoms? Are they made of this? Are they made of that? Just what are things made of? Not a question of the dynamics of evolution, but just what are things made of? And then you get to the 1600s, and you get to kind of the mathematical idea of we can write down a formula and time enters, but it just enters as a parameter. Then we get to the 1980s, the thing that was kind of brought to us by cellular automata, this idea of that time is a computational progression, that time is this irreducible computation. And that leads us to all of these phenomena and all this kind of, all these areas of Ruliology. And then now there's this new kind of idea of multi-computation, this idea that we have many threads of time. And when you have many threads of time, the only way that you can kind of understand what's going on is to have an observer who is somehow combining these threads to see what they think actually happens. And the observer for physics is one that has these characteristics, the important characteristics of computational boundedness and a sort of belief that they are persistent in time. Those two features of an observer necessarily lead to certain aspects of physics as we know it. Now, one of the things that comes out from this kind of notion of multi-computation is many application areas, which we're just starting to explore: metamathematics, chemistry, molecular biology, evolutionary biology, neuroscience, immunology, linguistics, economics, machine learning, distributed computing. It's really, I'm extremely excited about this, because one of the things that happens is, in a multi-computational system, you end up necessarily getting certain kinds of global laws that are like these laws that we have in physics. And you can kind of import then knowledge from physics to all these different areas. So, for example, in molecular biology, one of the possibilities is, well, the big sort of story there is, people imagine in molecular biology that there are these molecules, and what matters is the concentration of a molecule. We know that there are molecules that pack in a lot of information, like a DNA molecule. But one thing that I think is the case, and what's been suggested by this kind of multi-computation idea, is not just what concentration of molecules exist, but what is the whole causal graph of sort of progressive microscopic collisions between individual molecules. That causal graph can contain information that's important for molecular biology. And for example, in immunology, the suspicion is that that might actually be deeply connected to the way that immune memory works, and so on. So these are things that we get to start to explore by using this kind of multi-computational paradigm. This is something not specifically cellular automata, it's something that goes into this kind of multi-way generalization of cellular automata and other kinds of systems. I just mentioned, kind of the last thing I'll mention here is the thing that has been kind of my obsession for the last few months, studying the application of these ideas to you know, I'm going down, this is my to-do list for the next however long. This might be a 100-year to-do list. I don't know. I don't get to follow that. That's for the next generations to do. But the things that it's kind of a lot to study here in molecular computing and so on. But metamathematics is kind of first on the list. And what does that mean? I'll show you something. This is going to get posted in the next few days. It's not ready yet. This is about the physicalization of metamathematics and its implications for the foundations of mathematics. I think this is a kind of a bit of a fundamental rethinking of what mathematics really is fundamentally. And it's going to look a lot like, it's not quite a cellular automaton, but it's going to look very Ruliological. Because what we're thinking about is when we think about mathematics and we think about what's happening when we start off from axioms in mathematics and then we derive theorems, we can think that, for example, we start off with some formula here and then we can apply an axiom, we get another formula here. We might have a theorem that says this formula here, this expression here is equal to this expression here, because you can get from there to there by following these axioms. And so then we have this notion, there's a proof in this graph. This is a multi-way graph, actually, that just shows all possible derivations made with this axiomatic system. That red line is a proof. We can show what the proof actually is. You transform this expression to this. We're sort of turning the sort of the processes of mathematics into something that looks much more Ruliological, much more physical. So we can kind of go on, and this is a whole study of what happens and the emergence of mathematical structures and this notion of metamathematical space, the space of mathematical theorems and so on. And we can study these things. This is it's quite a lot of technical detail here because sort of connecting kind of the way that we typically do mathematics and we derive things from axiom systems. There's some issues of sort of connecting that to the way that multi-way graphs work and so on. Now, I will say, I should explain, well, okay, let me just get down to something here. This is kind of the structure of, that's automated theorem proving. There's things here about, oh gosh, this is a long post. This is a 250-page post, which will turn into a book. But these are kind of the space of mathematical theorems. This is kind of the connections between mathematical theorems. It's starting to look very physics-like. Let's see. Here are some axioms from present-day mathematics. You know, what is logic? That's semi-group theory. That's group theory. What is group theory like in these terms? That's the structure of the multi-way graph of group theory. And then we have to ask questions like, where is, in that multi-way graph, sort of the nodes here are theorems. And the question is, where are the famous theorems of group theory? Where are they distributed in that multi-way graph? And we can answer those kinds of questions. This is logic, for example. This is a multi-way graph representing logic. Those are some of the famous theorems of logic and where they are in the metamathematical space. This is, and so we start to look at, let's see, we've got other examples here. Maybe I can show you, gosh, I told you this is a long post. This is model theory, if people are into that. This is kind of the topology of proofs and the question of when you have two different proofs of the same theorem, you can end up with these topological structures. Let me just jump to, I'm not, oh, look at that. There's a cellular automaton. See, there's always got to be a cellular automaton in anything I study. That's an example of, it's a class 4 cellular automaton where we're discussing the way in which mathematics arises from something even lower level. When you're kind of drilling down inside the notion of, let's say, plus. Let's see if I can just find one more example of this. Oh, this is logic. This is kind of drilling down inside logic. Let's see. Oh, that's Euclid's, talking of Euclid, that's the theorem structure of Euclid, starting from the axioms of Euclid and deriving the last result in all of Euclid after 460 theorems is the fact that there are 5 Platonic solids, and the derivation of that involves this graph effectively. Let's see, what was I going to show you? I was going to show you that's in a formalized system for mathematics that's the proof of the Pythagorean theorem. That's the theorem dependency graph for 6,970 intermediate theorems proving the Pythagorean theorem from the axioms of set theory. And it's interesting to see, what is that structure? What kind of a thing is that like? And what's kind of interesting, because sort of relating to cellular automata and so on, is what's happening. The underlying stuff here is just Ruliological stuff, but somehow out of that emerge things like the Pythagorean theorem, where we kind of have an interpretation of that. This is actually showing some common results of. This is showing the Pythagorean theorem uses, if you unroll it all the way, it uses modus ponens 10 to the 36 times. So it's a very bulk use of kind of the underlying axioms when you really roll it all the way out. This is what's underneath plus. This is decomposing plus into the operations of set theory. You can go even lower than that and decompose that into things like combinators and so on. And what you're doing is you have this kind of giant soup of kind of computational processes, and you can fish out of that soup these things that correspond to operations that we know about in mathematics. I'll just show you just for fun. These are, let's see if I can find a good one here. This is metamathematical space, and this is showing in this, at this axiomatic level, this is showing the different fields of mathematics laid out in mathematical space. There are some famous theorems of mathematical space. So that's, but I just want to say the underlying thing that is the sort of the underlying big result here is this physicalization of metamathematics. So I should explain one other thing, and I really want to wrap up in a moment here, but this is the idea of what we call the Ruliad. So in our physics project, we have this notion of there is a rule, it's applied to this hypergraph, it evolves the hypergraph, and the large scale effect is like physics. But then we might ask, why this rule and not another rule? And that might be very confusing. But we realize we're applying this rule in all possible ways. Let's make it even more general than that. Let's apply the rule, let's apply not only that rule in all possible ways, but all possible rules. And so you might say, well, how on earth can you make anything kind of, how can you have anything that has any structure when you apply all possible rules? But actually, that's something that something hasn't really been studied. But if you look at, we can kind of get this concept of the Ruliad here. This is kind of the entangled limit of everything. You say, apply all possible rules, make this multi-way graph showing what happens with all possible rules. But what will happen is that sometimes two different rules will evolve to the same state. So that kind of gives you that equivalencing, gives you structure in this Ruliad. The Ruliad is the entangled limit of all possible computations. And it's a very big object. It's an object that intersects with the kind of upper limits of kind of Grothendiekian higher category theory mathematics, but it's an object that you can study in its own right. And in a sense, everything we're doing in Ruliology are sort of slices of little pieces, little samples from this Ruliad. And the thing that we realize is that physics is what happens when an observer with certain characteristics of, for example, computational boundedness and time persistence, when an observer like that, embedded within the Ruliad, observes the Ruliad, you inevitably get certain features of physics, the core laws of physics that we know. So that's a pretty important, cool thing. But here's the real sort of kicker. This Ruliad not only represents physics, it also represents mathematics. And so this exact same story applies there. There is an observer of the Ruliad that gives you not physics, but mathematics. There's a mathematical observer of the Ruliad that whose conclusions from the Ruliad are mathematics. And so one of the biggest results there is this idea in physics. One of the things that's surprising is that there is a notion of space, that it isn't the case that we're just saying, oh, everything is made of all these, gazillions of atoms of space. We have this idea that there is this sort of continuum-like notion of space that we can kind of move through. And so the question is that's a very fundamental observation about physics. and about the way we as observers of physics sort of sample this Ruliad of what's going on. And the question is, what's the analog of that in mathematics? The analog in mathematics is the very fact that we can think about higher level mathematics, that we're not dealing with mathematics down at the level of individual axioms and individual 10 to the 36 instances of modus ponens and so on. The fact that we can go up above that and imagine that there is a mathematics where we can talk about the Pythagorean Theorem and we can talk about right triangles and things like this. The fact that we can do that without always dropping down to this axiomatic level or even below an axiomatic level where we have to kind of define what the real numbers are and so on at every step. The fact that there is a higher level mathematics, I think, is the same fundamental phenomenon as the fact that we perceive space in physics. So in other words, this is connecting, this sort of physicalization of metamathematics is connecting the fundamental fact that mathematics is possible with the fundamental fact that we have a notion of space and we can make kind of predictions about what will happen in space. So anyway, that's my latest excitement, so to speak, of studying this this particular kind of application of essentially multi-computation to the physicalization of metamathematics. All right, I should stop there, and I'm very happy to take questions or have discussion. I would think of that as a bit of an update on cellular automata and things that grow from them. And I just, I want to emphasize again, there is just so much to study in this computational universe, and so many things. And by the way, we're going to be doing a bunch of things in the next little while to kind of help stimulate this field of Ruliology. We plan to launch a thing we call the Ruliological Society, and I'd like to invite those of you who are interested to be involved with that. One of the things that's also happening, it'll be the 20th anniversary of this big book in May 14th of this year, and we're planning a whole bunch of things in connection with that. Actually, I've been doing a weekly live stream about different chapters of the book. I just did chapter 4 of the book. Coming next week is chapter 5 on two-dimensional systems. So invite people to join that if you can. All right. Well, thank you very much, and let's. I'm happy to take questions or comments, and I don't know if you want to just unmute and ask them, or put them in the chat, or however you would like to do it.
Yes, questions?
Hello, sir. Oh. Hello, sir. My name is Supriti Kamilya, and it was a very interesting lecture, and I'm very happy to hear from you. Sir, actually, I wanted to ask you something that for a chaotic CA like rule 30, if we add one information to a stable system, it shows chaotic behavior in space-time diagram. But if we use other configurations, say like 0, 1, 0, 1, 0, 1 like this, then the behavior will be periodic. So in that case, can we say that chaos in CA is configuration specific? But actually, we say that it is rules. The rule is chaotic. But can we say that it is configuration specific?
It is what specific? Sorry, configuration specific. You said
configuration specific. That is the initial state. That is 0, 1, 0, 1 like this. So is it the initial seed specific, or it is the rule that is chaotic? Because
right.
Like 0, 1, 0, 1 in this initial state, we get periodic behavior.
Absolutely right. So I mean, what happens is there's kind of this whole okay. So there's a rule, there's an initial condition. There's a question of whether, for example, you can ask questions like, for generic initial conditions, what will the rule do? Well, let's say, I think you were just mentioning, I mean, if we make an initial condition for rule 30 that is periodic, let's just say we make, I think you said 0, 1, we just make, I don't know, 40 copies of that, and we just flatten that out, and we just say, okay, there's a bunch of zeros and ones. Now, we can easily predict what this is going to do, because we have some a system of size 2. So this is going to let's run it for, let's say, 40 steps or something, and let's just show this. Okay, this is going to do something very, very trivial here. because it has no choice. It just the underlying structure of the rule does this. Now, actually, an interesting question. Okay, so now we're going to do some Ruliology here. Let's replace part of this. Let's replace let's replace 40 by, let's say, 1. I don't know whether that's a 1 or a 0. We'll see. Oh, there we go. Look at that. Okay, so now, okay, this is already interesting. I didn't know it did this, actually. What we're seeing is on that background, there is, if we make a defect in that background, we'll start seeing more complicated behavior. Let's make a bigger version of this. Let's say 400 steps, and let's go ahead and let's do that 400 here. Let's see what happens. Okay, so what's happening there, and I know I've seen this before. So for Rule 30, I've seen this before. There's a line here of sort of where there's a kind of line between the periodicity and the more complicated behavior, and we can start studying that, and that will be an interesting question. And let's say, for example, let's say we change this to 100. Okay, let me just change that. I bet this is a oh, look at that. That's bizarre. Oh, I know what happened. 100 evolves to all zeros, and so necessarily it produces a behavior that's just like the original system. So let's say 110, for example, and let me change that to a 1. Oh, I think it's going to be the same thing. 110 just evolves. That's like, just like here, necessarily this will be periodic. So similarly here, it happens to evolve to 0. So when we put in this defect, we just get back the standard result. But you know, when you're asking, when we say chaotic, it's not a great word, because it's been sort of confused, because chaos theory is really a theory of the amplification of small perturbations in initial conditions. So, for example, if we look, let's pull up the NKS book. We can, let's see, I think this probably talks about it. Yeah, this talks about sensitivity to initial conditions. And what we're seeing here is this is sort of characteristic of different classes of cellular automata. We have change one bit in the initial condition. In class 3 cellular automata, we get this kind of continually expanding region of change. That's kind of sensitive dependence on initial conditions. And we get different kinds of things with different types of systems here. But what sort of classically thought about, there are some standard class 3 cellular automata showing this sort of sensitive dependence on initial conditions. When we when we think about, for example, where does randomness come from in a system? There are different sources. You can have the randomness from the environment. You can have the chaos theory version of randomness, like when you flip a coin, why does it come out randomly? The reason is, I think I even have a picture of that here. The reason is that as the coin is flipped and it gradually slows down and eventually it falls on one side or the other, what's happening is the precise initial velocity determines whether it's going to come out, you know, heads up or tails up. And it's because you are sampling, because you're sort of sensitively dependent on that initial velocity, that the thing seems random. It's in a sense not intrinsically random. There's nothing intrinsically random about the coin. It's just that the initial conditions get sampled. But it turns out that it's actually not very common for systems to work that way. And you can kind of find systems that do that. Cellular automata often have that feature, but cellular automata have the much more important feature that here's an example of something where it's kind of a hard, you're looking at hard spheres and you're saying, you know, as they bounce off other spheres or other circles, they will be, they're sort of they'll bounce back some multiple of what came in, and so that will lead to this sort of sensitive dependence on a small change of initial conditions. But it's a much weaker phenomenon to get randomness from initial conditions than it is to get it from the intrinsic behavior of the system. And that sort of intrinsic randomness is the big phenomenon of Rule 30. And there are features of I mean, as you're observing, there are things you can do, like making the whole system periodic, that prevent that randomness from occurring, but generically it will occur.
Okay. Thank you so much, sir.
My pleasure.
Hi, this is Colin. So a great talk, a great inspiring talk.
Thank you.
I have two questions out here for you. So one of the things that you showed, the hypergraph and the connection between maths and physics in that very nice graph. So you pointed out certain points in the graph which are examples of theorems that we know about, correct? So there
Yes.
are many such nodes which represents theorems that we don't, quote unquote, know about. So in some sense, does that actually also tell us that those are theorems which might be useful, which the quote unquote the maths community does not know of?
That's a good question. So the big story is there are, you can start generating huge numbers of theorems. You can do it automatically. Let me maybe show an example here, if I can pull that up again. Let's see. I wonder whether the navigation already works. We'll find out. Let me see. This is a, as I say, this isn't posted yet, so there's still many glitches in it. These are theorems of logic. So you can enumerate all possible true theorems of logic. Not too difficult to do that. Things like, and the ones indicated with red are theorems that are given names in typical logic textbooks. And so essentially what one is interested in, what happens is there's a giant ocean of true theorems. The question is, which ones do we humans care about? And we may very well not have found all the ones that we might care about. But for example, in the case of logic, we can say, it's a fairly closed system, so we can say, which ones do we care about? Turns out there's actually a fairly simple criterion here. Turns out, I was surprised by this, I found this out in the 1990s, that the theorems that we've given names to are precisely theorems that cannot be derived from ones earlier in the list. So in other words, there's no sort of structurally simpler theorem that implies this theorem. This is giving us new information about logic. And that's happens to be a criterion for which theorems do we consider interesting. Now, when you get to these other kinds of cases where we're dealing with sort of more elaborate mathematical systems, absolutely, there are tons of theorems, and knowing which theorems we will think are interesting is in a sense the art of mathematics. I mean, the sort of this physicalization of mathematics says it's easy to generate all the theorems of mathematics. The question is, which ones do we want to kind of associate, for which ones is there kind of a human narrative to tell about what's significant about those theorems? Let me maybe show you one example of how that works out. Let me see. Show you this. Find it. 1 second here. Where is it? Here we go. So in a Ruliological way, in the year 2000, I was interested in what's the simplest axiom system that represents logic, Boolean algebra. So I did a big Ruliological study, and indeed that's the simplest possible axiom system for Boolean algebra, where the dot represents the NAND operation. So now the question is, how do you prove that? Well, at the time I proved it using automated theorem proving, and the automated proof is this complicated thing. It's printed in the NKS book in 4-point type. It's this long, complicated thing. And in the 20 years that have gone since then, nobody has been able to kind of reduce that proof to something that is human understandable. So the proof is It's this complicated proof where there's a whole bunch of lemmas. And the question is sort of, is this mathematics the way that us humans think about doing mathematics? This is a mathematics that can be generated by a computer, and where there are lots of lemmas that are produced. Here are some lemmas that are generated. But the question is, what's the sort of human narrative associated with that, that mathematics? It's very similar to the question. So for example, here, these lemmas that I picked out here are ones that seem to be important in this proof. They're not lemmas that I think we particularly know or care about. They're lemmas that were important in this proof. And it's kind of analogous to, you know, when you have a deep learning system, a neural net, and it learns to recognize cats from dogs, and you say, how does it work? And it turns out that it's got this distinction somewhere inside the neural net. It's discovered that it's a useful distinction to look for, you know, corners of this type in the image, but we don't have words for that. And it's the same kind of thing in mathematics here, that we're looking at sort of this universe of possible theorems. Some of them we have kind of a human narrative to describe what's going on, and some we do not. And I think that the way we think about it now in terms of this kind of metamathematical space, well, in the end, everything sort of boils down to this Ruliad, and we're asking, what kind of observers can we be of this Ruliad? What kind of slice are we taking? What kind of things are we noticing in the system? This is rather abstract stuff. I'll give you an example from physics that's perhaps a useful analogy. So in statistical mechanics, in studying a gas, you could say, let me be an observer down at the level of molecules. I can see where all these molecules are bouncing around. That's what I know about. But we know that for us human observers, we're on a larger scale, and we mostly conclude that the gas laws are true. We mostly think about pressure and temperature and velocity in the gas. We are kind of operating at a higher level, and so we are the laws that we care about are these laws that are appropriate for us as large-scale observers of the gas. And the question of what kind of different mathematical observers will conclude about the Ruliad that represents all possible mathematics is a super interesting question. I mean, what kind of mathematics is, you know, are there completely different ways to think about mathematics than the ones we currently have? I should say, by the way, that in metamathematical space, one of the things that probably is a consequence of these ideas about the physicalization of mathematics is uniformity of metamathematical space. And what that means is probably that there are these dualities that we know between different areas of mathematics. You know, algebra and geometry have a correspondence. You know, we know from, you know, the Langlands program or category theory or whatever, that there are these correspondences between different fields of mathematics. The guess is that that is a generic phenomenon, that it is basically a consequence of a certain kind of uniformity in metamathematical space, that there is a necessary reformulation of one field of mathematics in terms of another field of mathematics. And that's, and so those are kind of, but this question about what is the slice that some particular kind of observer of mathematics will take, very interesting question. And it's something which I think is a way of formulating kind of the way forward in mathematics. I should say that the sort of the mathematical observer, like the physical observer, has certain kind of rather human constraints. You have to kind of, the mathematical, well, this computational boundedness constraint is one of them. But the mathematical observer, this is a complicated subject. Sorry, and there's much to say about it. But it's kind of like in physical space, we exist at some place in physical space. We know about kind of the universe near us in physical space. There's also a notion of Rulial space, of kind of what slice, what kind of interpretation, what kind of rules do we attribute to the universe? And we can imagine not only moving around in physical space, but also moving around in Rulial space, thinking about kind of different ways of describing the universe, different samplings that we could take as observers. And that kind of motion in Rulial space is something that we have done. We haven't done much motion in physical space. We've only got, you know, a few astronomical units away from sort of where we started, so to speak. But there's sort of a question in Rulial space of what does it mean to move to sort of a different description system for the universe. And that that question for mathematics is, well, I should say that doing Ruliology is essentially jumping around in real space. It does not give you, when you kind of go out and you just study some simple system, you don't necessarily have a human connection. You don't necessarily have a way to make sort of human arguments about it. You are discovering what's true, and then it takes sort of a big effort of Ruliology to get to the point where you can make principles to understand that. I think we're going to run out of time soon, but I'm sorry, that was you asked a very interesting and deep question.
Just
about
a
which
follow-up question on your the physics part of your formulation, the current project that you're doing. You seem to completely discretize both time and space. And
that's correct.
And what is your thought on the impact of the continuum or physics in future computer science? Computer science is mostly maths, but do you see an impact of physics in computer science in the near future?
Oh, yes. Oh, yes, very much so. So our formulation of this discrete hypergraph and the evolution of the discrete hypergraph and this idea of multi-way graphs, this is giving us right now an interesting new formulation of distributed computing. So there have been all sorts of efforts to try and make kind of a way of formulating what distributed computing is like. Usually when people do distributed computing, their main obsession is, let's make sure that not too many things are, that there are no kind of race conditions, that we synchronize every so often, that we get to the point where everything is synchronized and we as human programmers can say, and the next step will be this. What is happening from physics is this realization that we can have a truly distributed computational system where really different things are happening in different places, just as happens in the physical universe, and understanding kind of how to think about that computationally. And these multi-way graphs are the story of how to think about that computationally. I should say, as a phenomenon we call causal invariance, which is a generalization of the confluence property of term rewriting systems, or the Church-Rosser property of mathematical logic. That property, causal invariance, is basically saying different paths that you take, confluence is saying different paths you take through this multi-way graph will always end up in this, can always get to the same place. That property of this generalization of confluence, this causal invariance property, which is also equivalent in computer science to eventual consistency in databases, distributed databases, things like that, that property gives you relativity in physics. That property is the property that gives you relativistic invariance in physics. And so what that tells one is, for example, when one thinks about that in terms of computer science, in physics, we're used to thinking about different reference frames. We're used to thinking about boosted reference frames. We're used to thinking about different solutions for different gravitational fields, things like that. All of those ideas can now be imported into thinking about distributed computing. And so you get to start thinking about ideas like, I am programming in a certain reference frame. This is my distributed computing system, and I'm going to make these assumptions about what I assume to be simultaneous. And I can make a relativistic transformation that gives me different assumptions. And that's another way to look at essentially the same underlying computational system. So that's an example. I mean, in fact, right now, one of the things, okay, so another right at this moment thing that we're working on is, and for anybody who's curious, we live stream most of the discussions we do about this. I think we have another one even coming up tomorrow about multi-computation and the practical sort of applications of that. The thing that, okay, so the current obsession in that regard is this idea. So in Wolfram language, the basic idea is the fundamental structure of the language is it's making transformations on symbolic expressions. That's fundamentally what the language does. Those symbolic expressions can represent algebraic formulas, they can represent molecules, they can represent all kinds of things. But in the end, the language is basically making transformations on symbolic expressions. That was kind of the idea from 40 years ago, which has been the idea that's allowed us to build out this whole computational language. But one thing that I never figured out 40 years ago is there is a particular order in which you're doing those transformations. You say it's kind of like it's roughly a depth first kind of way of traversing things. Not quite that. It's a bit of a generalization of that. But essentially, you're saying, okay, let me just show one example of this that I studied in Combinators. So again, Combinators are a very Ruliological kind of business. This is so Combinators, people may know, they're a very simple basis for computation that was invented in 1920 by Moses Schoenfinkel. And one of the things that happens is you have these transformations for these essentially symbolic expressions. It's kind of a super minimal version of Wolfram language. And you can have transformations that represent sort of standard operations like Boolean algebra and so on. But the thing I was going to show you is, let me see if I can find it. Yeah, here we go. So with Combinators, you're doing these rewritings, but there are many possible sequences in which you can do the rewriting. And these in computer science, they have names like leftmost, outermost, and so on. These are different, essentially recursive evaluation procedures. And what we learn from kind of this way of thinking about things, see if I've got an example here. Maybe up here I have an example. Yes, what we learn from this way of thinking about things is these are multi-way graphs. So these different evaluation strategies correspond to different ways of picking paths through this multi-way graph of all possible transformations. And so one of the things that I'm now very interested in is in standard Wolfram language, as in, I mean, I don't know, you could pick, I mean, Wolfram language is a very clean instance of kind of pattern-based transformations on symbolic expressions, but you can imagine sort of functional programming or some other such thing being sort of a special case of that. This is, you can say, you're asking the question, what are all possible transformations that you could make? And then you can make statements about, for example, logic programming, for example, is basically saying there are many possible transformations and we're going to pick the one path that does best for certain purposes. Let's say we have a game, we're doing some game, we've got some different possible moves in some game, we want to find the path that optimizes something. The multi-way graph represents all the possible game tree moves, and then there's a particular path where we get the thing we want. Probabilistic programming, for example, says we take a slice across the multi-way graph and we say what are the probabilities based on path, number of paths and things that we get to a particular place. So you can kind of reformulate a bunch of these ideas in computer science in terms of multi-way graphs. But the thing that I'm particularly excited about right now is, you know, Wolfram language and sort of any programming languages right now, they'll take one path. And now from the physics project and from our understanding of quantum mechanics and the physics project, we get to talk about what happens if you think about all paths. And then what kinds of things, what kind of computation can you do when you look not just at one path, but at many paths? And I've studied that a little bit for multi-way Turing machines and so on. But this is, this is another, it's a very deep subject. But I would say that in terms of it's a very deep subject that we're just opening up. So it's really fun because there are you know, zillions of obvious questions which we don't know the answer to, and you know, we can relate. These things are much simpler versions of things like pi calculus and communicating sequential processes and things like that. Those are vastly complicated, more complicated versions of what we can kind of meta model down to these multi-way graphs. And from studying the properties of these multi-way graphs, we can then pull back up to understand things about distributed computing. And so that's, and yes, I think there's tremendously rich things to be done there, and ways in which we can import ideas from, I mean, in a sense, much of our physics project imports ideas from mathematical logic and from computer science into physics. We can now go the other way and take ideas from physics and import them into computer science. And I think that's going to give us some really powerful ways to think about distributed computing and about sort of the approach to programming distributed computing systems. But this is still very much a work in progress. And You know, I 40 years ago, I was really curious about these things about evaluation orders and different possible ways to evaluate recursive functions, and it didn't solve it back then. And I think we're finally within sight of solving that problem. So I'm really excited about that.
Sir, myself, Shutava Chatterjee Shortcut. I want to ask you a question, sir. Sir, actually, in real, sir, am I audible?
Yes, yes, a little bit echoey.
Sir, okay. Sir, in any physical or biological real-time systems, some sudden changes may occur that may be depending on the system constraints. That system constraints may be known. But if we want to go or model the CA, the system through a CA or cellular automata, how can I put the constraints in real time? Or is it possible to change some parameters, or we can introduce some parameters to the system so that we can change or control that changes of the cellular automata space-time evolution, sir?
Okay.
Is it possible?
So first point is, you know, traditional models of things tend to be full of numerical parameters because that's the way traditional models have been made. They've been made with equations that are based on numerical concepts. And so when you see existing models, you know, this idea of changing numerical parameters, that's very typical in those kinds of models. I would say that the real most powerful use of cellular automaton models is to understand the essence of a phenomenon. More so, there are cases where you can study kind of quantitative issues, but this idea where you have a parameter and you change it. Let me show you one example that came from the NKS book. So this is, let me just find this for a second. This had to do with snowflake growth. And, you know, we've got growing snowflakes, and the question is, what is the essential, what's the meta model of growing snowflakes? And you can ask, you know, well, we change a parameter, we change the rate at which the snowflake is falling, the humidity of the air, all these kinds of things. But what's the essence of what's going on? And what one realizes is the essence is there's a hexagonal grid that's being created by the underlying crystal structure. And one can think of it as when a piece of ice kind of forms on the edge of the growing crystal, it releases some heat, and that inhibits ice from forming nearby. That's the basic phenomenon. Now, you can say how much heat, you can change the parameters, you can do all these kinds of things, but the essential phenomenon is this kind of growth inhibition from when there's a piece of growth, it inhibits growth nearby. Okay, so given just that phenomenon, we can then make this kind of meta model of snowflakes. And by the way, the results we get look awfully like real snowflakes. And we can make quantitative predictions because in these snowflakes, we have these little holes that form from the arms coming together. We can say, what's the density of those holes and so on. And we can work that out. And this model happens to give us good results on that. But you know, it's more important, the place where cellular automaton models really do well is when the phenomenon is complicated, when it's not easy to characterize it just in terms of a few numbers, and you can capture the essence of the phenomenon using this simple computational rule, more so than saying, I'm going to get the number 7.4 out of this or something. Now, if you're asking the question, in a running cellular automaton, can you change its behavior by making changes to the, you know, by changing the values of particular cells? That's an interesting question. I studied that a bit in the NKS book. I'm trying to remember where that is. I'm going to guess it's in this section here. Let me see, where is that? Maybe it's here. This is just showing, well, this is more showing if you add kind of noise to the cellular automaton, what happens. But you could do sort of less, you could do small perturbations, and you could say, how does that affect the pattern that you get? And yes, that's an interesting question. If you say, I want perturbations that will behave in a very particular way, that's going to be really hard to figure out because of computational irreducibility. Computational irreducibility makes it both hard to predict what this system does and also hard to control the system, to specify, to try and determine what the system is going to do by kind of tweaking it. But you can certainly, you know, an example of where you can have sort of parameters that you can study a bit like this. For example, I studied fluid flow with cellular automata, and where you've got a two-dimensional cellular automaton with just cells which have these states that correspond to, you can think of them as like particles going in different directions. And there, the initial condition, which you kind of put these things down perhaps at random, but with a certain overall velocity. And so that then gives you, when you look on a large scale, gives you something like that corresponds to fluid mechanics. But that's a case where you've got an underlying cellular automaton rule. And in this particular case, just by changing the character of the initial conditions, you're essentially moving through different regions of physical space. So for example, I think I might have a picture here of what happens as you increase the Reynolds number of flow in the cellular automaton fluid. First of all, you just get these, oh no, actually this is a function of time. You're getting just these eddies form behind this plate, and then gradually the eddies break off and you get this complicated wake behind the plate here. But these are things which, where you're effectively just changing the initial conditions for the cellular automaton, and you're doing so to correspond to what happens in the system. I might say that in our models of physics, we do the same thing, and we've started to be able to do things like simulate black hole collisions by looking at the structure of space-time, by setting up initial conditions that correspond to a structure of space-time that corresponds to two nearby black holes, and then we can see what the consequences of that are. So I guess my feeling is it's better to think about changing the initial conditions than changing the underlying rule, and the real power of the underlying rule is in capturing sort of the essence of the phenomenon, particularly when there's complex behavior involved.
Thank you so much,
Okay.
sir. So we probably made you tired already.
That
Yeah.
it's I thought we would run out of time here, but it's
But
been a pleasure
listening to you is always such an enriching experience that there will be lots of questions to ask you. But unfortunately, we don't have much time left for you to.
That's fine. Well, I just would like to say that let's see, can we take one more question, or did we run out of time? If there's maybe one more thing, perhaps we can fit that in, or we can call it a day. For you, it's a day. For me, it's a night.
Sir, I wanted to ask you whether you were saying about Euclidean space, whether if you take the same kind of rules over hyperbolic space, how much difference in behavior we can observe? Have you?
Okay, I have. So one of the issues about cellular automata in hyperbolic space is hyperbolic space is very big. That is, you know, in ordinary Euclidean space, effects that, you know, two effects can't get that they're kind of, you can't fit in that many effects, so to speak. In hyperbolic space, you can have this whole tree, you can fit a whole binary tree that exponentially expands into hyperbolic space. I haven't looked that much at cellular automata in hyperbolic space. I guess I've looked a little bit, well, let's see, what have I done? I think it's a very interesting area. Let me think about this for a second. It's one of these things where I bet there's a note in the NKS book on hyperbolic space, and I've already forgotten. I've certainly looked at it in connection with our physics project, but that's a little different than cellular automata. Let me just, I have to look this up, because it's, you know, in the 20 years since I wrote this book, I kind of can forget. Here we go, hyperbolic space. I knew there would be I just knew there would be something. Of course, there's something about this, although I don't think I really explored it well at all. This is, by the way, I do encourage people who are interested in the NKS book, which you can find online. By the way, we will have a code hopefully by the time of the 20th anniversary in May, we will have code for every picture in the NKS book available directly from the book. But this is the kind of thing I think you're talking about, is looking at a cellular automaton that where the neighborhood structure corresponds to this kind of tree structure. I haven't looked at this very much. I would, as I say, I would guess that some of the phenomena that come from sort of repeated interaction will not occur here. So for example, okay, so here's something I can say. One of the things we do a lot in the physics project is to study causal graphs, to study when this effect happened here, how does it, this event, this update happened here, how does it affect other updates that happen? What is the set of causal connections between updating events? And what we often find is that the structure of the causal connections is, let's see if we can find an example here. The structure of the causal connections, let's see. Where is a good causal graph? Here we go. Well, these are some causal graphs that represent kind of where's a good one? That represent kind of, that's not what I wanted. Oh, these are a little hard to understand, but basically every event here, these yellow dots are events. And this is saying it's like each event is a function being executed, and each event needs input from a previous event that was another function that generated certain outputs. And so we kind of think about things in terms of the dependency of one, what needs to be available in the system for this event to occur? What other events have to have occurred previously? Now, in a cellular automaton, I'm pretty sure I have a picture of that here. Let's take a look. The causal graph for a cellular automaton is rather straightforward. This is the causal graph for a cellular automaton. Is this the causal graph? Yes, this is the causal graph. It's a little complicated to see, but basically what's happening is this cell here depends on, let's say, these two cells here. And so there are causal edges that connect those things together. In the case of and there's sort of a whole knitted together causal graph. In the case of hyperbolic space, the causal graph will be a tree, because the causal graph of what affects what will just have that tree structure. I probably even have a picture. Let me see if I've got one. Maybe I do. Hyperbolic space, there we go. That's a good thing to start with. So these are hypergraphs that produce hyperbolic space. And they produce, this is the structure of the graph, but the causal graph, which I might show somewhere here, maybe not. Sorry, I don't have that here. Graph will always be a tree. And so that sort of limits the amount of interaction that you can have between different parts. Now, yeah, I mean, interesting question. If we had more time, maybe we could do a little bit of a live experiment and study this. But study it. Figure out the Ruliology of hyperbolic space. That's definitely an interesting thing to do. And I think there are probably spaces that are negatively curved as hyperbolic spaces, but that aren't quite, maybe they're trees which have some cross connections between them that you could start to study. I'm not sure. And just the general question of cellular automata on graphs has been studied much less than cellular automata on lattices. And the main issue for graphs is, well, which graph are you going to pick? And so some graphs that are interesting, I think, are Cayley graphs or other vertex transitive graphs, where every vertex has the same local neighborhood. And those are cases where you can have sort of an analog of a cellular automaton, again, very unstudied, I believe, and something that would be interesting to know more about. All right, we should wrap up there. So yes, I thank you very much, and I'm sure you'll have an interesting conference, and keep studying cellular automata. There's so much to explore, and the things that one studies from cellular automata today, 50 years from now, 100 years from now, people will be really glad that, and less time than that, but in 50 or 100 years, the things that people study about fundamental questions about cellular automata will still be very important. And that's a great, I find that a great sort of encouragement to study these kinds of fundamental Ruliological questions that, you know, one really is down at the foundations, and that's something that will be a surviving kind of thing. All right, well, we should wrap up there. So I should disappear, and time for me
Thank you so much, sir.
Thank you very
Nice
much.
to see you.
Thank you.
Great. Okay. Bye-bye.
Bye, sir. So